All right, we have a homework due tonight, so I'm gonna try to get another homework out today. And I also want to reveal the first programming project that won't be due for a bit. It's probably 2 or 3 weeks out before that project is due. But I at least want to give you the ability to get started with it because it can be a little bit, especially if you don't have a ton of experience or history with dynamic programming, because that is going to be the solution that approach that you will need. All right, we were doing fun things. We were looking at the differences between NPDAs and DPDAs and the languages that they can recognize. I guess I should also say that you'll have a study guide by Friday for an exam week Friday. Another thing that's starting to be on the edge of consideration for the future as well. So here was a language that we tried to tag a deterministic approach to, and that fell apart pretty quickly. We can see from the grammar's construction that when we look at L1 and L2, we have to, on the first character, already have made a decision between which of these languages the string will adhere to. And there's no way to know that deterministically. We have to take a deterministic approach to it, where we explore them in parallel, fork the process on that first character, and see if one of those processes can return something of interest that actually accepts it. So this kind of logic is absolutely possible in an NPDA, but it is not possible in a DPDA. And I do not target this course toward kind of a math proof oriented style that you would expect in a true math course. I want this to be more of an undergraduate computer science targeted course. So my care is the intuition, and I'm hoping that the way that I describe this helps make the intuition clear. It's very different from a math proof oriented argument, and a mathematician would absolutely be yelling at me right now saying that I am not doing this justice and I am leading people astray from the real way or the true way to think about anything that involves theoretical math. And to them I say, yeah, but who's using that anyway? At least in computer science. Theoretical mathematicians, they use it on a daily basis. But to me, as a kind of intuitive learner, a logical learner, I think that if you can explain the intuition for it at that level, that's probably where you need to be able to utilize this in a computer science field. You will never need to write the proof for that unless, of course, you are doing formal verification for programs. Most people don't go off and say, how can you mathematically prove that my program is going to be correct for all possible inputs? Unless you decide that that is exactly what you want to do for a living, in which case, maybe take a second look at this and try to understand it theoretically and technically. So since the non-deterministic context-free language and the deterministic context-free language are different language classes, it makes sense to consider, well, all right, well, we can't just map context-free grammars to the same class of language that a deterministic pushdown automata would accept. So what changes need to be made to grammars to represent that same class of languages that a deterministic pushdown automata could accept? The reason we even care about them in the first place is that we can parse them efficiently as opposed to non-deterministically, which requires a search. As soon as we have that determinism, we can search that space in a linear fashion rather than in a fashion that requires us to go through what we did with CYK to put that together. So because there's only one possible move at each state in a deterministic pushdown automata, we are able to guarantee that the number of grammar productions that we need to look through before we know whether or not the string is in the language, depending on what we can do to grammars, is going to be finite. It's going to be something proportional to the length of the input string. So as we go through the input, as you would expect, we match part of the input to the characters, the terminals that the grammar is producing. And then there's going to be some kind of non-terminal that represents the inputs that we haven't seen so far. And this is another example of where something like Rybach normal form is useful. because you, for every production, can immediately parse the terminal, and then what's left at the end of that is just a sequence of non-terminals. But more so than Greibach normal form, we need a new classification that is called a simple grammar. And a simple grammar is exactly what maps to this deterministic pushdown automata idea. It just has a similar kind of form or idea to Greibach normal form. It's the simplest connection to something that we've seen before. So a simple grammar just says there's only one choice of production to apply at the current input symbol. I keep remembering there's one slide in this, and when I don't fix it, that I failed to animate. Every time I teach this course, I get to this slide and it's like, crap, I still haven't animated this. So here's a dump of information. So simple grammars. It's wonderful. They can represent all aspects of syntax and programming languages, just like context-free grammars could as well, but they're a little bit simpler. So one of those grammar types is LL grammars, and study those very late. It's what the second to last thing we're going to study in this course. So we're going to come back to how exactly LL grammars work, but I can give you a little bit of insight into what that looks like. So with an example grammar, LLK, which is there's LL1, LL2, LL3 up to LLK for some K. It says how far ahead into the string do we need to look to be able to determine for sure which production to apply. And if there is a limit to that, like 2 characters, then the grammar is LL2, and we can look at a table of look-aheads up to 2 characters and be able to say, okay, whenever I see this sequence of characters AB from this non-terminal S, I know that I need to apply this production instead of that production in order to be able to map it. So we will see exactly how to do that later in the course. And of course, the rest of this is also not animated. So I think, honestly, rather than spending a ton of time talking about LL grammars at this point, we'll come back to it. And that will make a lot more sense than giving you kind of an introductory, cursory glance at it. But we'll dive into this in probably more detail than you would ever care to know at the end of the course. But the takeaway from them is that most programming languages that we have out there can be fully defined by an LL grammar, which means we can create a linear time parsing algorithm for the parsing step of the compiler. Yeah, a lot of the efficient compilers that are out there are written using LL. And so we'll return to this when we study compiler parsing in more detail for how that is actually done. Oh, so yeah, the course is split into kind of 7 weeks or so of content that gets you ready to talk about compilers. And when we talk about how compilers actually work, we can look back on these kinds of problems to say, what is parsing? What is this step? Why do we care about this in terms of the translation between a higher level language and a target, either assembly language or machine code or byte code? And we'll be able to see why we have studied this. It seems like just a lot of useless garbage until you do that, but when you see it actually in play, it is really cool how it breaks down into everything that we have discussed so far this quarter. So the application is coming.
I mean, I think some of the problems are fun.
I know. I try to do this like programming problems should be, in that you have a problem to solve, and as you solve those problems, you start to get a sense of some interrelations between the problem formulation and a solution that you might not have seen if you weren't thinking about it in terms of problem solving. I think that's an intriguing approach, I guess, for it turns something that if you're just looking at this as theory would be horribly boring, and it turns into something that's a little bit more fun to play around with. Hopefully. At literally everyone else in the class, what are you both on? All right, that's it for this slide deck, which means we are getting into What fun.
Wanted to mention,
Oh, no. More pumping lemmas.
okay, none of the slides after exam one are posted.
Yeah, I need to get to that, don't I? I've been bad at maintaining Canvas this quarter because there's so much maintenance to do across everything. If that's ever the case, if you notice that, just send me an email and that pops to the top of a stack of things to immediately go do and play around with. Excellent. More pumping lemmas. Why would we ever come back to pumping lemmas? We're just starting to understand regular pumping lemmas. Why would we talk about more of those? We'll refresh because it's something that you're thinking about on your current homework assignment. So what is the pumping lemma for regular languages? Yeah.
It's basically a proof that's like, hey, this can't exist because if you choose a certain size DFA of whatever you name it, then that can't represent every single possible string in the language, no matter how big you choose the DFA to be.
Yeah, it's a proof by contradiction that says we're going to assume that this language is regular. And moving forward with that assumption, we're eventually going to derive a contradiction. If we assume that there are M states in the DFA and that the string can be broken down into the portion of that string that is getting to the first loop, iterating a loop in the DFA and then getting to a final state, because we need the ability to represent strings that are longer than the number of states in the DFA. That's necessary with any infinite sized language. So that means that there must be at least one loop in the DFA. So we pick a string that iterates that loop, and then we can pump that to I equals 2, where we iterate that loop twice, or 0 times, or 10 times, or something based on M times. And that allows you to eventually create a string that cannot be in the language. And if that DFA existed and accepted a string that needs to be in the language that you identify, then when you pump it, you find that that DFA would also accept a string that is not in the language, which creates your contradiction. But in general, regular languages have a repetitive pattern to them. There's the portion of a string that leads up to a loop, the ability to pump that loop, and then a portion that goes from the end of that loop to a final state. So we know if there's a string in the language not adhering to the pattern, the language can't be regular. For context-free languages, instead of looking at the state machines like we did in regular languages to think about them as a DFA, breaking down a path through that DFA, instead we're going to look at grammars because it's going to be much more intuitive than trying to look at pushdown automata. So how does the context-free pumping lemma arise? How is it related to the regular pumping lemma? I said the hardest part of this course was understanding the regular pumping lemma, and I stand by that. This is not as difficult as understanding the regular pumping lemma for the first time, as long as you understand the regular pumping lemma. The extensions that we make to it here are not actually that insane, but they turn the proofs into something that is a lot more tedious and is a lot more work. That said, the baseline is understanding the regular pumping lemma. That is going to be the difference between this making sense and this being spoken in some language that you have never seen or heard before. So when looking at a grammar now instead of a state machine, the way we want to think about this is we're going to have recursion between a non-terminal and itself. Via some number of productions, we are going to expand a non-terminal like A into a right-hand side for A. Somewhere inside of that, we're going to expand non-terminals and expand non-terminals until we get back to an A. And that creates the loop that we would have found within the DFA. If any of you have taken data structures from me, is there anyone here who did that? Dang. It's been too long since I've taught data structures. But depending on who you took it from and how that was taught, is there a sense of the intuition between the fact that loops and recursion represent the exact same logic?
Like, to an extent, yes, it just depends on what flavor you write it in.
Yeah, so I really like using the not as example of recursion, but an example of why recursions are into this idea. Because Tower Boy is just a few lines recursively, but it requires, at least in Java, the instantiation of a stack object and keeping track of memory over time within your loop's history. Your loop is going to be looking at and making operations to a stack. The programmer think about instantiating a data structure and manipulating, utilizing the method called. But there's no problem that can be solved with a loop that can't be solved with recursion, and there's no problem that can be solved with recursion. And a DFA, we can think of recursion in a grammar when we go from in a strings derivation, seeing a non-terminal, to being able to expand that into some characters. We have something like S arrow. Very simple recursion. It's already there in a single production. We can, as we do this, remember this from A to the N, B to the N. We can now say S arrow A S B, and now this is when we go to expand this, there's a subproblem. That was the subproblem that we just focused on, and that becomes the new problem, but we've generated something on the outside. So if we went from right to left instead of left to right, we would actually be doing something like calling a subproblem on part of the string, throwing away the right left and recursing on the middle, and then doing something with that, finding a right and left side, recursing in the middle. So it maps exactly to recursion as you have seen recursion in past classes. So it doesn't have to be just a right-hand side that has it. This S could go to A. This A can go to something, who knows. And now we have the ability for S to produce an A to produce a B to produce an S. And by the time we do that, we've hit that recursion where in some number of applications of this, we find ourselves back at a place where we could have started. So like before, where we had the XYZ, where the XYZ was getting to the loop, iterating the loop, and getting from the loop to a final state. Now we're going to find that this maps to a 5 tuple instead of a 3 tuple. There are going to be 5 things that we need to do. We need to, and slides will talk about this, but we're going to have U, V, X, Y, Z, where U and Z are what get us on the outside to that first recursion. So this would be something like we generate. Let's give you an example that actually makes sense. Yeah, if I do a very similar language. Note that this is just A to the N, B to the N, such that N is greater than or equal to 1 now instead of 0. So the U and the Z are the forced A and B before we get to an associated recursion. So it's the characters that we generate, kind of like X was in the regular pumping lemma. This is what gets us to the recursion. Any characters that we have to see on the left-hand side or the right-hand side that get us to the point where we're ready to do that recursion. Does that make sense? So in some grammars, that's going to be empty if the recursion is right away. But in some grammars, that's going to require that some symbols exist on the left-hand side and the right-hand side before we reach that recursion. U and Y, in this case, are the characters that's generated by the recursion itself. So as we go from the first time seeing this symbol to the recursive next time we see that symbol, we also produce some characters potentially on the left and right. So that would be the representation of U and Y for a single recursive pass, just like Y was a single pass through that loop. UY, in this case, VY in this case, is going to be the characters on the left and right that are produced by a single iteration of that recursion. Finally, X are is the set of characters that's produced going from the recursion to termination in the grammar. So you can imagine that this lambda becomes something like AA, where now there are more A's than B's in the middle, but it's the characters that are needed. Once we finish this recursion of going A to A to A to A, this is what terminates the string so that there are no non-terminals left. And we have a string that's in the language. So the characters that get us to the recursion, the characters produced by the recursion, and the characters that get us from the end of the recursion to the acceptance, the string that's in the language. And this version of that string is going to be what maps to a context-free grammar. Does that make sense? That's a lot to throw at you at once to visualize why, but
I think so, but like seeing an example would probably
Yes.
help a lot.
yeah, we're definitely gonna get there.
So, can these be strings, not just single characters?
Yes, yeah, these can all be substrings, arbitrary parts of information. So if you can have an arbitrary length size of something here before the recursion, so B would be more than one character. Same thing with any of these. They can be empty, they can be more than one character, arbitrary size. But when we pump now, there are two places that we pump. It's at the places of the recursion. So the pump, instead of being X, Y to the IZ like it was in regular languages. Wow, I cannot draw today. We have U, B to the I, X, Y to the I, Z as the pumped string. Because what we have control of is the number of iterations of that recursion. Everything else is held constant. Kind of like the X and the Z were held constant in the regular language. Getting to the loop and getting from the loop to the final state, both of those were constant strings. The U and X and Z in this case are all constant, and the recursive aspects, the V and the Y, are going to be what get repeated some number of times, or 0 times.
Can either of those be empty? Or they get just a regular.
They can. You can recurse, yeah, on either V or I. It's just the length of VY has to be at least 1. Just like the length of Y had to be 1. There has to be some recursion. That recursion has to produce at least one character, but it doesn't have to come from both sides. It can come from one side or the other.
So we can pump lambda as many times as we want on one side
Yeah,
or the other.
exactly.
For this example, would A be R X? Or
Yeah, I should
I'm
I'm going to
B's?
differentiate these characters so that we can see that this would be your U, this would be your Z, this would be your, this C would be your V, this D would be your Y, and this AA would be your X. Getting to the recursion, iterating the recursion, getting from the recursion. That is X. I really can't draw. Apparently I'm still in that in my head. And yeah, there's your X. All right, any other questions before I dive into kind of some of the restrictions on this and then diving into some examples? So that's really the entirety of the rest of the complexity of it. If you understand the regular pumping lemma, then a lot of the intuition from that carries over. So here is just kind of talking about the recursion part of it. If we have a non-terminal that produces some terminal characters on the left-hand side and the right-hand side, and we can get from there to some terminating point, then we have the v and y from what I just talked about and the x from what I just talked about. So these can produce x, vxy, vvxyy, vvvxyyyy as we iterate that recursion 0 times, 1 time, 2 times, or 3 times. Big differences that end up mattering a lot in terms of how we construct our proofs is that there are 2 pieces of what gets pumped. And the pump can occur anywhere in the string rather than just the first m characters. So that becomes a huge difference between regular pumping lemma and the context-free pumping. The reason for this is the restriction that we're going to find is that the length of vxy, the entirety of that recursion plus the, it's just the length of vy. The length of that recursion can be at most the number of productions in the grammar rather than the number of states in the DFA, as long as your grammar is in a form where each production adds at least 1 terminal, which is always possible to do. So let's take a look at the actual official pumping lemma language. We start by saying let L be an infinite context-free language. Then there exists some positive integer m. So we use the exact same m that we did before. So, but now instead of representing the number of states in a DFA, it starts to represent the number of productions in a grammar that is in a particular form that we're not going to care too much about, because you can always take a context-free grammar and put it in that form such that there are m productions in it once it is in that form. So don't worry too much about exactly what that is. Just call it m exactly as you did in the regular pumping lemma and carry it through. Then we say there exists a string w that is in the language that we care about, such that the length of that string is greater than or equal to m and can be decomposed into uvxyz such that it is vxy. The length of vxy is less than or equal to m, and the length of vy is greater than or equal to 1. So vxy is just the characters between the start of the recursion and the end of recursion. Plus, this is just a single pass through that recursion, the number of characters that go from the recursion to the end of the string. That can be at most the number of productions in the grammar. Then the length of vy that says the number of characters that are produced from a single pass through that recursion has to be at least 1. The recursion has to generate at least 1 terminal. Otherwise, we can infinitely recurse and produce nothing, which means that we can spin forever, and we can't allow for that. It's the equivalent of having an infinite loop in a program and calling that program, this program will always terminate. No, if you go into the infinite loop, you won't terminate. So we cannot have an infinite loop in our grammar. That is not continuing to add more terminals, at least. So here's kind of the idea. We start with a single start non-terminal. U and Z are what is produced by the time we hit the first iteration of that recursion. Then V and Y are what's produced as we go from that non-terminal back to itself, iterating that recursion once. And then X is what's produced going from that non-terminal to termination in the grammar that produces the string UVXYZ. Does that make sense? So that's the example. There's still a such that when we do the pump, UV to the I, XY to the IZ, that also must be in the language for all I. So if we're trying to create a counterexample for this, we would say assume that this language is context-free, and you would be looking to derive a contradiction where you identify the I such that UV to the I, XY to the IZ is not in the language. The reason this works, there are a finite number of productions in the grammar, infinite number of strings in the language. So that means that we have derivation trees of arbitrary length, and a way to visualize this visually, because I think that's also necessary, is something like this. This might help you. So if we're producing the string as we go, we start with that start non-terminal. By the time we hit the first recursion, we've produced u and x in some capacity. So these are the terminals that get produced as we go from s to the character that we're using to represent our recursion, the non-terminal that does our recursion. Then we have b and y that are produced from there to get back to a, and then we have the ability to go from a to termination. But note that we can repeat this part of this an arbitrary number of times. So that's what creates that derivation trees of arbitrary length, because we can copy this and paste it an arbitrary number of times above it or below it. And that creates, or even take it out. And that creates, we take it out, that is I equals 0. If we duplicate it once, that's I equals 2. If we duplicate it twice, that's I equals 3, etc. So it's kind of a visual representation of how a grammar produces the associated string UVXYZ. And of course, these are all sequences of terminals, not the actual characters UVX, Y, and Z, but the point holds. How are we doing? Seems like we're at the point where an example might be useful. Because I love the pumping lemma game so much, and I get so much fight back whenever I do this, how does thinking about this as the game change? So, as before, we can't instantiate M. We want to carry M all the way through the proof. But the way that we discussed this, and it still holds, is player 1 is going to pick M, the number of productions in a grammar that can represent this language. Player 2 then picks some string adhering to the constraint that it has to be longer than M. Player 1's turn again chooses the decomposition of VXY. Before we said that they chose the decomposition XYZ. Player 1 got to choose the entire decomposition. But now player 1 just chooses where VXY is in the string. But it's no longer constrained that it has to be in the first M characters. It's just constrained that the length of it, the window of it in the string, can only be M characters long. So this is where you as player 2 have the power to choose a string that is wide enough, it's long enough that a sliding window of size M through that string overlaps the fewest number of potential cases, because the more it overlaps, the more cases you're going to have to write in your proof, which is generally annoying or sometimes can completely break the proof and make it unprovable. Player 2 then chooses the value of I once player 1 has chosen that decomposition, such that UV to the I, XY to the IZ is not in the original language that we used. And so the goal of the game, once again, is to prove that player 2 can always win the game, or that player 1 can never win the game. Not an iteration of this where player 2 beats player 1. It's that player 1 was doomed from the start. It's like you playing chess against Magnus Carlsen. Good luck. Doomed from the start. Or me playing chess against Magnus Carlsen. I shouldn't make that an only you thing. Any of us are doomed. I can appreciate the confidence, but it makes me think you might be a narcissist.
There was that one guy I beat him.
Sorry?
So there was that one guy I beat him.
Yeah, that was true.
Whether or not
None of us are that talented.
whether or not it was a legitimate win is up for debate.
I saw some vibrator.
All right, so let's take a look at an actual example. We'll see if we can get through this in the remainder of class. I think we can. So We're gonna revisit our old friend A to the N, B to the N. It turns out that if we slap a C to the N on the end of that, it becomes difficult to do with a context-free grammar. In fact, so difficult that it may be impossible. Take a second and think about that. Why would A to the N, B to the N, C to the N not work with a context-free grammar or a non-deterministic pushdown automata idea?
Now you have to have, if you're looking at from a context-free grammar, you now have to have two sets of recursion. One for two letters and one for the last letter.
Yeah,
And then you can't measure how long the first set was done compared to the second set.
yeah.
So now you end up with the same problem we end up with the regular language because you can't store the data.
We can't validate the number of Cs. We have to choose whether we're pairing the A's and B's, we can figure that out, or the B's and C's. Think of yourself as having a stack. What do you do when you see A's? Put some stuff on the stack. It says how many A's that we've seen. When we start seeing B's, we're going to pop things off the stack. And that maps the number of A's that we've seen to the number of B's that we've seen. Then when we see C's, how do we figure out if they're the same number that we had seen before? You could try to add something on top of the A's and then something on top representing the B's, and then you could map the C's to the B's, but then you don't know how many mappings there were there to map them back with the A's from before. So there's no way to store that information. We need one more piece of memory to store off like an integer of how many we saw, and there's no way to do that. If we could say n is less than or equal to 10, then we could. But we would need an infinite amount of memory that scales with the number of possibilities that n could count in order to represent this with just a stack and a finite size state machine that carries around that infinitely sized stack. So that said, what should we pick as our string? So if we're doing this in terms of the game, player one comes to you and says, there are 7 productions in the grammar, there are 12 productions in the grammar. We're gonna try to prepare in advance and say they're gonna come to us, and no matter what they tell us, we should be ready to handle that argument. So from this planning stage, they come to us and say there are M productions in the grammar. Well, how do we want to structure our string based on this concept of M?
Do you have to pick A, B, and B, D, and C again?
That becomes a floor or something to pick. This will absolutely work, and we're gonna roll with exactly that. A to the M, B to the M, C to the M. As long as we don't have something that is less than M here, we're good. But if we chose A to the 2M, B to the 2M, C to the 2M, that would be okay. 10M, A to the M squared, B to the M squared, any of those would actually technically work. Because when you put a sliding window across that of size M, how many possible cases are there for where VXY could possibly be?
You can only take a snapshot of 2 of the letters, right? Because you can only see
Up to 2 of the letters. Yeah, so there are 5 cases because of that. And we will see that a lot of context-free pumping lemmas do this. They break down into way more cases than you want to handle. But frequently those cases combine such that an intuitive argument for one maps directly onto the other. So you can imagine now that, I forget exactly how much of this is on the slide so that I don't have to draw it out. We do say A to the M, B to the M, C to the M. Player one can only pick a VXY in these 5 cases. Only A's, only B's, only C's, a window that has some A's and some B's, a window that has some B's and some C's, and that's it. Those are the 5 cases. And I was hoping there was a visual for this, but I'll draw out the visual because I think that will help. So we have some A's, some B's, some C's. We can either see all A's, all B's, all C's, or a window containing some A's and B's and some B's and C's. Why can't we see some A's, some B's, and some C's?
because we don't have a big enough window.
Yeah. Yeah, it would take at least, if there are MBs, we would need 1 C and 1 A, so M plus 2 characters to fit a window where we had some A's, some B's, and some C's. And that is bigger than the window that we allow. VXY can't be larger than M. So that puts us in these 5 cases. So to prove this, we need to say, okay, if player one comes back to us and chooses a VXY, they could pick one that is in any of these 5 cases. So we have to identify an I for each of them. So let's move forward, assuming that player one comes and chooses this A only. So there's a sliding window, they say VXY is all A's. What does this mean, and how could we show that we can break that by recursing somehow on V and Y that are all A's? Yeah.
Recursed with only A's, we'd be becoming more A's, and then the A to the M wouldn't.
Yeah, so if we choose an I that is greater than 1, let's just say greater than or equal to 2, then the structure of this string is going to be A to the M plus the length of Vy times I minus 1, but I just assume that they picked I equals 2 here, so we have M plus the length of Vy, B to the M, C to the M. And this is obviously not in the language because as we saw in the last couple slides ago, the length of Vy has to be at least 1. So we're adding at least 1A to this string, and now this string no longer adheres to this form. So we've created a string that is outside of that language by saying, if the recursion is in the A's, and we recursed 1 extra time, everything else about that path stays the same. We create the same U and Z. We iterate the V and Y 1 more time, the recursion 1 more time, and keep X exactly the same. So if we go back to that visual diagram, we just duplicated the V and Y portion of it, keeping the U and Z and the X constant. There has to be a way to generate a string in the grammar in exactly that way. But when we do it, we see that the structure of it cannot adhere to the language, which means there's a way in that grammar to produce a string that's not in the language. So what that tells us is that the recursion can't be in just A's. But a very similar argument exists for the recursion in just B's, because we set I to be greater than or equal to 2, and we see that we get A to the M plus, sorry, still A to the M, B to the M plus the length of Vy, C to the M, and that kills. That is an option. So the recursion cannot be in just B's. Very similar argument for C's, the plus the length of Vy just moves on to the C's. We can eliminate that case. So player one can't pick that. This becomes our proof. We kind of have a contradiction that we derive for each possibility that player one could pick. So how do we show it for AB or BC? There are easy ways to do this and harder ways to do this.
I mean, by the assumption of where the window is, either it's going to include only A's, only B's, or mix of the two.
Yeah,
So either way, you're either going to end up in the previous situations where you're boosting A or B, or you're going to be boosting both of those, and C is still going to be
yeah,
itself. So as long
yeah.
as
The intuitive argument is we're going to be modifying either the number of A's, the number of B's, or both. And if we do that, then there's no way for them to all be equivalent anymore. So you're going to compare the number of A's plus B's to being 2 times the number of C's. That's probably the best way to go about this. Is it saying we would have to be adding either an A or a B or a combination of A's and B's or more than that. And regardless, what this language is telling us is that the number of C's, twice the number of C's, has to be equal to the number of A's and the number of B's. That breaks when we make some modification to the number of A's and B's, because again, the length of Vy has to be at least 1. So there will be a modification of some kind to the A's plus B's portion. If you don't do this, then it breaks down to something that's a lot more complicated. And so I'm just going to kind of draw this out and try to avoid taking this kind of path, because it's going to lead to way more work than you want to deal with. And that would be, all right, we're going to break this down into kind of the A's and the B's. We know that VXY is somewhere over this, but we don't know the length of v or the length of y. So now we have to break this into the cases where the length of v is empty. The length of y is empty. So there's nothing in v, there's nothing in y, but the nothing in v, so v can either be, vy can be on the a's side, and if that's the case, then that's this problem that we already solved. If vy is on this case, then that's this case, so that's already been solved. We could have v be all the way on this side, y be all the way on this side, which creates the ability that we are mapping either both a's and b's up. But then v could be empty, which again, y, just y, that's the b case. If y is empty, that's pumping just v, which is the a case. So now I'm down to putting us back to what we've talked about 4 times so far. But that doesn't consider v being in the middle of this somehow, or y being in the middle of this somehow. So that when we pump v, that means y is over here. So we're creating more b's than a's when we pump vy. Or that y is in the middle, overlapping both, and v is over here, which will produce more a's than b's. All of that can be lumped into a single argument, considering of when we look at this string, we can use the equality of 2 times the number of c's is equal to number of a's plus the number of b's. And if you do that, then this is way simpler. All of these cases that I'm generating for this one case fit under breaking this equality. So there's a lot of intuition in a lot of these, and you can make your life a lot easier if you think of what are all of the cases, what do the cases share in common, and how can I produce an argument such that I only have to argue something once instead of way more times than you want to. If you get marked down on these kinds of problems, the most frequent issue that I see is an incomplete argument, where you argue for some of these cases and try to put an argument for these last 2 cases, but you don't consider all of the possible breakdowns of vy for it. So if you start this process is really hard to finish. If you start this process, it's really easy to finish and it handles everything. And again, a mathematician would probably yell at me for saying that. But the intuition is there. Any questions on solving this? It's gonna overlap some of the stuff, yeah, but that's basically the breakdown of how you would go solve a context-free pumping lemma type of problem. Break it down into the cases, then argue something for each of those cases such that you end up with a complete proof. Intuitive proof. Again, mathematicians would yell at me. I feel like it should have been a Friday, like you need a weekend after that kind of lecture. But I have office hours starting now for people who have homework related questions. Come see me and I will be happy to help you.